A very warm welcome to all of you to SupportVectors Meetup research paper reading. I see a few new faces here, so I would like to mention how we do that. We meet every Wednesday at 7 p.m. usually. This paper reading session we have been doing for the last couple of years. All the paper readings that we have done, well, I wouldn't say all, but 1 year's worth we didn't actually keep track of. But for the last 1 year, or more than a year, all the paper readings are there in the SupportVectors YouTube page. That's it. Another announcement that I would say is that we are, maybe this is a 1 minute that I'll take to advertise our course. We are offering a RAG, in-depth RAG course, which is coming up on February the 24th, and that is this. So I'll just let you guys absorb it, that if you go to supportvectors.ai, we are offering a RAG and AI search bootcamp. And usually the sessions that we do before it are preparatory to it. It helps you warm up and get started. And that bootcamp is a 4-month bootcamp. It's very rigorous. It brings about 2 of the dominant themes of 2025, namely RAG and AI agents, because we are going to do a lot of AI agents also in the RAG course. So mark your calendar. If that interests you, go to supportvectors.ai and look up this bootcamp, RAG and AI Search Bootcamp. That's coming up starting on February the 20th. Okay, so with that out of the way, I would like to get started to the research paper reading. Again, this is a public talk. It will be posted to YouTube and I don't know where else. So be careful not to divulge any personally identifiable information or anything that is company confidential. In case you do so, let us know immediately. There's a time window of a few hours in which you can scrub your whatever information you want us to take out. So with that in place, hold on longer comments or more reflective discussions for the very end. Nevertheless, as we do the paper reading, as questions come up, please do keep asking. It's perfectly all right to keep interrupting, because this is supposed to be a joint paper reading. So with those things in place, let's get started now. This paper I chose not because it's sort of, there are very few research papers which have come out that are not already dated. This one came out on 15 January, so it's just about a month old. And being a month old, it covers almost all the techniques that we know about RAG. RAG is Retrieval-Augmented Generation. What it stands for is that you can ask a question from an LLM. It can answer, but it suffers from 2 problems. One is the data. Its knowledge is dated. It's dated to the day the LLM was trained. And the second problem with an LLM is that it may hallucinate. What it says may not be factually correct. And just today, I believe, it was BBC that came out with a report that said that even when you give an LLM, the state-of-the-art LLMs, to summarize their articles, they found that there were defects in significant defects in the summarizations. 51% of the time, the majority of the time, it would miss something perhaps the most significant point of the article, it would have entirely missed. Right? And sometimes it would hallucinate and add things that are not there. And there's a host of problems that they discovered. We are talking about the state-of-the-art LLMs applied to, frontier LLMs applied to articles which are of high quality, the BBC News articles. So it does speak to the fact that LLMs as tools, we have to be very cautious in using it in the enterprise. So given the hallucinatory nature of LLMs, given the fact that their knowledge is dated, the recourse has been to back the LLM or augment the LLM with a search, with a retrieval technology. By retrieval, what we are saying is that when a query comes, we would do a normal search into either the web or our local databases or our code base, right, or structured data, or any one of the many data information sources you would go to. You would bring the top end results, top K results. Then those top results, you would then feed it to an LLM and say, answer the questions in view of these facts. So you would insist that the LLM use those facts. When you do that, then two benefits are supposed to accrue. They don't actually come about, it turns out, unfortunately, but it does make a huge improvement. One benefit is that your answers are not dated. That part is true. If you have given it more recent information, then it will take that information into consideration in answering the question. The other aspect is whether it would hallucinate. The unfortunate reality is it nevertheless hallucinates. But if you just use a naive form of RAG, but if you are more nuanced about the way you have created your retrieval augmented generation pipeline, then the hallucinations are quite significantly mitigated. You can force the machine to keep going back and produce evidence from one of the source documents. So one way to think about it is that in a RAG system, you have two key ingredients. The two key ingredients are, you have a retriever. Oh, sorry, what just happened? You have a retriever. You have a retriever system. The retriever system's job is to given a query, to produce the top K search results. Now, retrievers usually retrieve, you often go to multiple indices. You can use a dense retriever, that is a neural retriever. You can use your traditional BM25, the keyword retriever, like Elasticsearch, etc., as they used to be. You could go to the web. Sorry, what am I doing? Web. You could be looking through some structured data source, DB. And from any one of those places, you bring the data. Now, retrievers are complicated. They're not just one shot. You go and query those sources and whatever comes out, you go. The main problem that happens is that once you get many results from each of the sources, how do you decide which are the top K relevant results? So internally, they use some re-ranker to make it possible. But leaving all those complications aside, you feed this then into an LLM. You give this LLM and the user query. You give it the user query. You give the tuple. You say, and one more thing that you do is you give along with it a system prompt. It is a well-crafted prompt that you have written, telling that answer the questions in view of the search results that you are bringing in. Sorry, this I should say, query results, top K results. These things go into the LLM, and when they go into the LLM, in the most straightforward representation, LLM generates an answer. So this is one way of looking at it from a LLM perspective. Another way to look at it is from an information retrieval perspective. If I have a question and I go to a search engine and all it does is brings up the relevant documents, it's basically saying your answer is somewhere in there, go read it. Go explore those documents, those web pages, and you'll find your answer, right? And from an information retrieval perspective, I suppose it's good. It does retrieve the answer, but it would be much nicer for the user to get a answer itself, which is the additional functionality that LLM brings. Now, LLMs have two aspects to them. One is they are language understanding machines. They understand human language. And so if you give it a text and you query and system prompt, it should theoretically answer the question based on the search results. But besides that, there is also, it has parametric memory. In its weights and biases, those hundreds of billions of those are also stored a lot of information with which the machine has been trained, the LLM has been trained. So when it answers the question, unfortunately, you have two competing memories at work. One is the information that is coming from the top K results. You would call that retrieval memory, but it also has the parametric memory from which it may answer the question. And so sometimes people want the LLM not to use as parametric memory, but to predominantly depend upon the search results, in which case you do all sorts of techniques to have it pinpoint exactly which of the sources, which of the results led you to answer a query the way you answered. So this is a brief summary of simple RAG. Now, RAG, ever since it came out, it has become a dominant generative AI use case. I would say the most used and the most compelling use case in enterprise environments. It is inarguably beneficial because every organization is using search, and to transmute search into RAG has obvious benefits. It saves time. People don't have to go read those documents, and they can, and all those other things remain. So I would say, just like for before a generative AI, machine learning has a wide variety of use cases, but the way it touched people's lives in a dominant way was with the recommender system. Right? We use recommender systems for e-commerce, we use recommender systems for Netflix and Spotify, and so on and so forth, and many other use cases. Today, with generative AI, the dominant use case is RAG. There is a problem, however, with RAG. While we see the obvious, it's quite obvious that it is a useful tool, the problem is with the tool itself. Despite its promise, despite the fact that it makes a lot can be done if it works, it doesn't always work perfectly. In fact, the biggest source of problem is RAG remains an imperfect tool. So it has evolved over time. There has been such a huge set of research papers written on retrieval augmented generation that I have stopped keeping track of it. There was a time when I like to have printed out papers. So I would print out all the significant papers on RAG and store them in my folders, physical folders. After I had filled a whole shelf with RAG, I just stopped doing that. Right? And papers also keep getting superseded with new work and so forth. So I do stay in touch, but it is hard to stay in touch with every single thing that's coming out on RAG. So I thought that it would be good to pick a paper which is recent enough and which sort of gives a view of all of RAG, starting with the state of the art. Today, when we look at the state of the art in RAG, two big ideas come together or inform and make it powerful. Those big ideas are, one is knowledge graphs. And I'll sort of, before I go into this, actually this paper is more of a survey paper, and it doesn't quite do justice in explaining those concepts. So I will take some time to explain that with diagrams, and then we'll sort of walk through the paper. The key, I suppose I'll put it this way, the big ideas that come out are hybrid search, that uses AI search and the keyword search, and implicitly a re-ranker that figures out from all those search results what is the best to pick up. This is one key idea. Then we use graph knowledge graph or knowledge graph specifically. And so graph RAG has become a pretty big theme in RAG. And I will, when I explain to you, its usefulness becomes quite obvious. Indeed, it would be hard to argue why one would not use graph RAG. In a similar vein, the next big thing that has come about is AI agents. AI agents are important because they can help orchestrate a whole bunch of techniques that we have discovered over the years. For example, when query comes, the user query may be not explicit enough. It may need further transformation, right? It may need more elaboration before you send it to the search index. You may be doing things like hypothetical document embedding, which is that sometimes it is advantageous to take the query to the LLM, get the LLM's preliminary answer without even going to the search index, then use that answer along with the query to search into the vector indices, the search indices, to get a much more relevant answer. People have found it leads to much more relevant answers, and then retrieve that and then feed it back into the LLM and say, given all this information that we have, and now correctly answer the question. So there are a lot of techniques that have emerged in the RAG space. One of the paper readings that we did was Dragon, which looked at when exactly does a machine start hallucinating? When does a LLM start hallucinating? So one of the contentions of the paper was that you will see that the entropy, if you keep observing the token as they're coming out and looking at the entropy values, you would see that hallucination happens when the LLM indicates that it has less confidence in what it is producing, right? So when that happens, why not pause it there, go back, throw away that part, go back into the search index, know exactly what is relevant, go back into the search index, research for additional facts that can help the LLM answer the question or continue to answer the question with more confidence. So the literature on RAG is vast, and the techniques that people have come up with are quite amazing, actually. It's amazing how deeply people have thought. But there's one unifying aspect to it. How do you create an architecture in which all of those are put together? If you hardwired every single technique known to RAG, what will happen is your query pipeline will become prohibitively expensive. Suppose you ask something very simple, which is, what's the capital of California? That doesn't quite warrant the big guns to come out in response to that question. In fact, that might be simple enough. You can trust the LLM can answer without even needing to go into the search index at all, right? So then comes the whole question, well, how do we determine how much of the complexity to bring in? And that is where AI agents are very good at it, because they are in a way dynamic. They're making dynamic decisions. They can take the query and decide how many of the techniques to pass your query to answer the question, which of the search indices to go to in order to get the best answer. For example, if it knows this search index is specific to finance, right? And given the query, which is nothing about finance, for example, what's the capital of California? Why would you go to accounting or valuation documents? That wouldn't make sense, right? So agents are very good at making that sort of decision. And for example, it could be very good at using a classifier to tell which of the subjects this query touches upon, right? And then go to the appropriate indices. So the one way to think of it is AI agents create dynamic workflows. When they get the query, they think about it, and then they can orchestrate a dynamic workflow through which they can, a dynamic RAG workflow through which they can orchestrate the whole execution. In that case, you have the advantage that you don't unnecessarily bring up a lot of complexities. They also give you the flexibility of looping. The results, for example, when they come out, it can decide, AI agents can decide, okay, let's validate, is there backing for it in the documents or not? And so on and so forth. Right? So today, the big big ideas that are there that you want to incorporate into your RAG system are this. You want to have hybrid search, you want to have graph RAG, and you want to have agentic. So people call this sort of thing agentic RAG systems. And it could be variously called. It could be variously called. It depends upon where you put an emphasis. But this paper chooses to call it agentic RAG, Agentic Retrieval-Augmented Generation, and it's a survey of agentic RAG. So with this as a backdrop, this paper, the only reason I said is that it gives a structure for us to review the whole landscape of RAG. Beyond that, I felt that it had very much the nature of a survey in the sense that it doesn't contribute anything to original, actually. Its main value is it has put those, the whole techniques into a long list. So let us walk through this paper. The first is, what are the core components of retrieval augmented generation? So it speaks of the retrieval system, three components: the retrieval system, which is responsible for querying external data sources, knowledge bases, APIs, vector databases, etc., and getting some top-tier results. Now, they also mention a thing called augmentation, which I tend not to use the word. To me, this augmentation is something the LLM or something else is doing. But generally, I think of it as part of the pipeline. But they say process retrieve data, extracting and summarizing the most relevant information to align with the query text. So let's put that there. And then the generation combines retrieved information with the LLM's pre-trained knowledge to generate coherent, contextually appropriate response. Right? The way I would say it is that it uses language understanding to basically take the search results and craft an answer which looks like an answer to the user's question, right? In simple terms. So it makes search into a conversational interface. The evolution of RAG, and they talk about a naive RAG, and see, people's definition of naive RAG, advanced RAG is very, very subjective. So I wouldn't put too much value in the way these people have defined, but people say that the most simple RAG that you can produce is, for example, a wire up a simple search database. It's a keyword search, Solr, Elasticsearch, whatever, OpenSearch, and give the query to it, get the search results, and then with a prompt, system prompt, those search results, give it to an LLM. That they would call these people call it a naive search, and they say it uses TF-IDF or NBM25. These are keyword search retrieval systems. You would do that. Even if you do that much, clearly, and a lot of RAG adoption, actually, surprisingly, a vast majority of RAG adoption in the industry is literally this, because most enterprises are sitting upon Elasticsearch, Solr, OpenSearch, or some sort of a search engine over their documents, right? Therefore, just sort of shoehorning an LLM is a very low-hanging fruit over the search interface. And it is something that they have done. Its main limitations are that lack of contextual awareness. What do we mean by contextual awareness? This takes a little bit understanding. What it means is when you do keyword search, the meaning of the word may be different in different contexts. We keep using the classic example that is used is the word bank. Is it a river bank? Is it a financial bank? Or is it an airplane banking in order to align with the runway? So just keyword search on bank is perhaps not as useful as a contextual search that looks at the entire query text and understands that we are talking about, let's say, a riverbank, right? And retrieves results specific to that. In other words, that's a classic weakness, by the way, of the retriever system itself, and therefore of RAG or naive RAG. The weakness of the retriever system carries forward. We live today, of course, in the world of semantic encoding. We create a vector like text encoders using a BERT-like and a Siamese loss function or a contrastive loss function of some form. And by doing so, what we create are so-called semantic embeddings. When you do semantic embeddings, these are also called the dense embeddings of text. What it means is, and for those people, I'll just give a small summary. If you have a piece of text, what you do is you project it into a space given a text ti, and imagine that this text is talking about something. Let's say that it is talking about wildflowers. And there is another text which is talking about, let's say, California poppies. And then there is another text which is talking about repairing a car. Intuitively, you know that these two are similar topics, much more proximal topics than these two. These two are far apart. The repairing a car does not seem to be very relevant to wildflowers. And what semantic embedding does, and semantic embedding is of course done using a transformer encoder part of a transformer traditionally, which there are other ways of doing it. What you do is, let me call this T1, T2, and T3 pieces of text. Given a text I, it will produce a vector, one or more vectors. So I'll just use the word one, understanding that tools like Colbert, they use multiple vector embeddings, but let's just call it EI. So it produces a vector I in such a way that T1, E1, E2, which are about similar topics, are nearby, but the vector for irrelevant, a completely different piece of text, which is irrelevant to wildflowers, would be positioned in the vector space far apart. Right? So this is called semantic embedding, because the only way a neural network, a neural architecture, or in particular, it's a transformer encoder, which is the most common thing used these days, can do this is if it understands language and it has been trained with a contrastive loss to do such a thing, put similar things together. So that is, I suppose, what is being referred to in this thing, that it lacks contextual awareness, because an embedding, keyword search doesn't have the benefit of this semantic embedding. But if you use vector embeddings, a semantic embedding, you do benefit. So it is, in other words, far better to get results from a vector embedding. It's not always true. The counterexample is, and by the way, when we do the RAG course, we go over situations in which AI, neural, the semantic embedding leads to better search results, and situations in which keyword search leads to better search results. Generally, semantic embedding beats a keyword search most of the time. The few times where it doesn't is when the word given is too lacking in contextual relation. If you just give one word, well, now if you give one word, it could be any, there is no particular advantage that a semantic embedding has over keyword. So in situations like this, they sort of get matched, but in most other situations, semantic embedding does better. The second limitation they point to naive RAG is fragmented output. The absence of advanced pre-processing or contextual integration often leads to disjoint or overly generic response. So it has to deal with the fact that, see, let's look at the word bank. If one chunk of text that was retrieved, one document that was retrieved, is talking of riverbank. Another is talking about the financial bank institution and accounting, and another is talking about an airplane landing. You can quite plausibly say that is going to confuse the LLM in answering the question, isn't it? And so it might end up with sort of an incoherent answer, or not a very well shaped answer. It will try to incorporate everything. Scalability issues, keyword-based retrieval techniques struggle with large data sets. Actually, this point is not to do, I suppose. Well, again, you could argue that these things, Solar, Elasticsearch, OpenSearch, they're battle-tested technologies. They can deal with really large corpuses of data. So the scalability issue is, I wouldn't say that it's really that big an issue. They do handle it for all practical purposes at very, very large scales. So I would not put too much credence to that. Then you get to the, yeah, go ahead.
Sorry, in the previous section where you were talking about the fragmented output, right? And the example with the bank, I thought with the encoder and creation of the vector embeddings, it will place them properly in the vector space. So we should technically not get a mix of the airplane banking or the river
That is right. That is right. But remember, what did I say? Their definition of naive RAG is not to use semantic embedding, just to use keyword embedding.
Okay. Got it. Thank you.
And so they are pointing out that if you use keyword embedding, and I gave you an example of why you can end up with a piece of documents, one document talking about one meaning of bank, another document talking about other meaning of bank. And so the LLM will be forced to create a rather confusing answer based on those two documents.
Sure. Got it. Thank you.
That's the point. And so, see, these words, don't take them too literally. The only reason I picked this paper, not because it's the definitive work that establishes terminology in this space, but because I was just looking for a paper that itemized a lot of the techniques, and I thought I could use that to survey the techniques. As it says, it's a survey. Now, many people, like in my own opinion, I was surprised. For me, a naive RAG starts with vector embedding, right? Semantic AI, and goes from there, but they call it advanced RAG. And so their definition of advanced RAG is to use vector embedding. And as you can imagine, it won't suffer from the problem of contextuality. Contextuality is the strength of semantic embeddings. Nevertheless, because you also bring in, and it's always a good idea to bring in, well, I don't know if these people do that. Today, what we do is, no, I think they do it in Modular. So they're saying vector embedding and LLM makes it advanced RAG according to it. But let's forget the terminology. That's the next evolution. Then the people use, so guys, whichever house you go to or slide deck you'll see, you will see that people are making a vocabulary as they go along. But the point is that they're trying to differentiate through different techniques. And the important thing is to know that there are these distinctions. So they call this a modular RAG. A modular RAG basically means, let's say retrieval is one part. In retrieval, you may be going to many different search indices. Like I said in the beginning, you go here to many search indices. You can go to neural search, like dense embeddings, BM25 words. You could search the web. You could search the structured database. You could even call an API, right? For example, if you're looking for flights, you might as well call a flight API, right? To know how many flights are possible between two cities. So that is, by the way, the state of the art. Today, if you want to really create an enterprise-grade RAG system, a basic recommendation that we give is extend the definition. Remember that search need not be just in documents. It can be in images. It can be in audio, into video that you have indexed. It can be across APIs that you call dynamically. You may throw in a search engine to look into the web. And above all things, for us engineers, the most important source of documents, valuable documents, is the source code itself. All of this source code, like these days in the most of the IDs, we just write a question, and lo and behold, answers start coming out. What code starts getting emitted. That is one of the great use cases for RAG. It is essentially a RAG system. Right? It is using your existing code base as well as the LLM's own parametric memory of all the code it has seen to infer what could be a good solution to your problem. Yeah.
Question. So taking your example of the code base, I'm assuming that, let's say, take example of cursor. Okay.
Yeah. Microphone, please. Yeah. Would you please repeat your question? Yeah, it's on.
Yeah. So taking the example of the code base and specifically cursor as an ID, is it fair to say that when it is initializing the project for the first time, it is actually going through that encoding process? It's looking at all the source code and creating maybe something locally on its own embeddings?
Yes. Actually, there's a lot going on there.
So the prompt in the cursor ID is actually running a retriever locally in the local code base embeddings and then going out to the LLM?
Yes. See, what happens is that cursor sits upon VS Code.
Yeah.
VS Code is actually a marvelous piece of technology. They have a code server underneath it. What it has done is it takes your entire code base and builds an abstract syntax tree out of it. So there's a very coherent structure, very indexable structure, right? And that structure, because your code base, whatever it is, it will be what? The typical code bases will be 10,000 lines or something, give or take. Large code bases will be 1,000,000 lines or so, which for modern systems is nothing, right? It will index that. Given a query, you have the benefit of an LLM, right? And it is the joining together of your code base and the LLM's parametric memory that is basically RAG in some, but it's a really well done RAG.
So there's a local encoder, maybe it's your code server, etc., whatever that is. That's maybe the encoder. And the AST is kind of your embedding.
Yes, you can think of it like that.
And then you also have a local retriever in the cursor, which is retrieving from it locally. So the retrieve is not in the cloud server somewhere.
No, your code is never pushed to the cloud. Yes, it's local.
Okay, and then finally when it combines it, then it goes out to the LLM, augmenting that query.
And that is right. And you can also, I don't know exactly about cursor, but there are tools that will keep even the LLMs local. For example, you can connect to a local LLM.
Sure.
Right, so that it is all within your intranet, which you should do, by the way. If you're writing the very sensitive code, you should never let it exfiltrate. So that is it. That's it. So these people define the modular RAG as what I drew the diagram right in the very beginning, that you could. This is what the baseline diagram that I'd made. They call it the modular RAG. This is where we are. Right? Common sense says retriever should be as powerful as possible, retrieve from as many sources as possible, dynamic and static. Then you take the results, you feed it into that. Then comes the main part. The problem with this even modular RAG, which by the way, they give through this complicated diagram. What are the patterns here? Retrieve and then read, retrieve. I'll ignore all of this. The main thing is that it doesn't quite solve the problem as well as we are going to, as we want in reality. And so the compelling case for graphs and for agents. So to speak of the strength of this, they say key innovations are the hybrid retrieval strategies, tools integration. I mean, you can integrate APIs, databases, and so on and so forth. Right? And composable pipeline. So you can decide what things to put in your pipeline. Nevertheless, your pipeline is well defined. And this is, I suppose, the beginning point of how today we think of RAG. If we are going to do a in-depth implementation of RAG, and as I said, I consider 3 ingredients central to RAG. One of them is heterogeneous retriever, hybrid search, what I called. Very necessary. The second part for RAG systems is the graph RAG. Now, and the third part is agents. Agents, the argument is absolutely, I mean, in a way, it hardly needs to be said. Every part of the query, the pipeline needs mediation because it can create dynamic pipelines. The query may need improvement. If nothing else, it may have typos and whatnot. Right? You may contextualize the query by an agent looking up what is your role in the organization. Right? And based on your role may determine, for example, that you have authorization to the engineering database, but not to the finance database of the company. Right? So you shouldn't be privy to how the sales is going for this quarter, right? But you should be. You're totally right for you to go to this particular. So a lot of that, permissioning, etc., authorization can be controlled through AI agents, and it can do query transformations, and it can create the whole flow, and it can keep cycling through till it is convinced that the answer is good. Right? So the case for agents is so compelling that I would say it is hard to imagine why one would not do agentic RAG. Right? It is the state of the art. I would leave it at that. But I would like to explain the graph RAG a little bit. Why graph RAG? Graph RAG actually speaks to knowledge graphs. And I would like to talk, this paper does not quite talk about it, but I thought I'll bring it about because we are doing our own sort of survey of RAG techniques. Knowledge graphs. So what are knowledge graphs? Knowledge graphs comes from this. So what are graphs? More specifically in this world, because this thing relates to things like ontology, right? And people talk a lot about this whole field. They have been trying to systematize all of human knowledge, and they have been trying to create knowledge graphs. The two large public knowledge graphs that we know of, large-scale graphs that we know of, one is the Google's knowledge graph. And a manifestation is sometimes when you search for something, do you notice that on the search page on the right-hand side, a lovely box comes up with a lot of information in it. And that box is so informative that you don't even have to bother to go into the search results. Right? Try asking for something, like, for example, the Taj Mahal, and then you'll get a whole history and location and God knows, many things, or the pyramids or something. You'll get all the facts. You wouldn't even need to go to the search result. That is the Google's knowledge graph at play. Now, the other one is from Wikipedia, the Wikipedia organization, the DBpedia knowledge graph. So they have also tried to systematize all the knowledge sitting in Wikipedia into a knowledge graph. Knowledge graphs have the following properties from a functional perspective. If you do have a knowledge graph, oh goodness, you're the sheikh of knowledge, because it is valuable as hell, right? It can really help you in every way. Think you got a query and you can find all the related information that is pertinent to that query. And you use that to then search into a search engine. Do you see that? So it will help you do query augmentation, query transformation, or augmenting the query with further details, then go to the search engine to search for things, right? So that's a value of such a thing. The problem with knowledge graph is that it has been historically very arduous to build. So what is a knowledge graph and why is it arduous? Knowledge graph is a relationship between, it is entity, relationship, entity. So it's a triplet. That's how you think of it. So for example, I can say Sacramento is capital of California. This triplet you would call one atomic unit of knowledge, right? And a knowledge graph is an arbitrary set of these triplets, arbitrary large set of these triplets. As you can imagine, the larger the knowledge graph is for your field, if you have taken a field and you have taken every single entity in there and found its relationship to every other entity, if a relationship exists, you will end up with a graph, because this is a node, this is a node, and this is an edge. And when you take lots and lots of nodes and edges, what you end up with is a graph, right? Now, you would say, all right, big deal. What is so special about it? Well, two reasons to take it seriously. First is human knowledge is inherently hierarchical. You might be talking about one of the STEM knowledge, quantitative or analytical knowledge. Within that, you might be talking about, let's say, physics. Within physics, you might be talking about quantum field theory, right? Within quantum field theory, you might specifically be talking about a superstring theory, right? And within superstring theory, you might be, for example, talking about some specific thing. I'll just throw a word, Calabi-Yau manifolds, right? Which is a very, very specific topic within superstring theory. So human knowledge is hierarchical. Much more simply put, you might be talking about math. Within math, you might be talking about algebra. Within algebra, you might be talking about quadratic equations and how to solve quadratic equations. So human knowledge inherently tends to be hierarchical. And the good thing but not necessarily a tree structure. For example, that statistics, for example, if I say that we are doing linear regression, it's part of statistics, it's part of machine learning, it's part of medical science, it's part of just about everything where it is used. So it will have connections to just about every analytical field of knowledge, right? So it's a graph, not a tree, not a hierarchical tree, just to bring that fact out. Now, so it is a graph. And so suppose you have a query that touches upon certain nodes of the graph. It is very tempting, would it not, to pick up the siblings and to pick up the children, just a couple of them, to see if they are also relevant, and then go to a search index. Right? So that is one way to reason. That's actually a very naive way to reason about knowledge graphs. And I'm going to refine that idea a little bit more on how to do that. Because now I'll talk about what I call complex networks or complex graphs. See, and this is important actually, because I feel that the power of knowledge graphs truly comes from this. And one of the groundbreaking work that Microsoft did in their paper, GraphRag, specifically leverages what I'm going to tell you, a property of large graphs. Large graphs have structure that you don't see in small graphs. This was discovered actually, it's called the scaling law. There is a scale invariance present in large graphs. So that sounds rather mystifying words. It's sort of the work of Barabasi and so forth. Discovered that at the turn of the century. What it means is that it's the small worlds phenomenon. When you take a very large social graph, you realize that there are communities within communities within communities. If you look at human social graph, right? So, for example, you would notice that all the AI engineers, if you were to look at the LinkedIn graph, probably you would find that they are all sort of interconnected to each other. There's quite a high degree of connectivity within the AI engineers. But those AI engineers have some degree of connectivity within a larger community, which is, let's say, all the computer science guys, right? Or programming, the world of software, broader world of software and engineering itself, right? So that is upper level structure. And a lower level structure is within the AI community, you might find subclusters little subclusters. These are called sub-communities. A sub-community could be the computer vision community, the natural language processing community, the time series analysis community, the anomaly and fraud detection community, and so on and so forth, isn't it? So those people, they will form their much tighter relationship to each other. And that will be visible to you if you were to draw the whole social graph. Are we making sense, guys? So now, that is the structure, communities within communities, structure that complex graphs exhibit. For it, it has to be sufficiently large. Now, if you go about taking human knowledge or the knowledge within your organization, it will have a it will have a proliferation of terms. It will, if you were to build a knowledge graph, then you would imagine that it will be a rather large knowledge graph. Well, it turns out that that is good news, because if it is a large knowledge graph, what can you do? You can observe the communities that are forming and the communities within communities that form. So this was the work of Microsoft's GraphRag paper. And what they did is they said, okay, let's do one thing. Let us say that we are talking about, I'll just take something, quadratic equations. This is here, right? And it has a few siblings. It is there. What you do is every piece of document that is here, that is falling into this region, that community in the graph, you pick all the nodes. And then you ask which are the back documents from which this is coming. And then what you do is you use a LLM to pre-create a summary of quadratic equations. Imagine that a little couple of paragraphs you have written. Imagine, intuitively speaking, you have written about quadratic equations. Then you have written it about the next topic and the next topic. Now there is a parent topic, algebra. And you notice that that subsumes everything. That algebra, sorry, I should make it like that, subsumes all of this. What can you do from the summaries? All of these summaries, S1, S2, S3, can go towards creating a higher level summary of the algebra community, which can be used to create a higher level summary of the math community. Are we together? Community of topics. So you have hierarchical, and this, as you can clearly see, will do wonders for your search. Do you see this, guys? Right? Because if you go and index these communities, the summaries of these communities in your vector database, when you retrieve the answer to your questions, you're likely to get much better answer. And the empirical evidence is, yes, it is so. And the GraphRag paper, and I should say papers because they have done subsequent work on that, it does illustrate the point. Your question, please go ahead.
Yes. How do we find the entry point for first node?
Oh, so I will explain that. Hold that thought in your mind. Actually, how do you find that? It's very easy, because the query that you have, you shred it itself, and you say, what are the relevant nodes in the knowledge graph that it pertains to? For example, you are saying, what's the capital of California? Oh, California, the term. You can go directly into California node and see what are the neighbors. And you will notice that right there is the answer sitting. Sacramento is capital of California. Do you see? And that is what Google was benefiting from in the pre-LLM days. The trouble was that creating this is all wonderful. Like I said, if you have a knowledge graph, and if you can even not just blindly use knowledge. By the way, I must emphasize this point. Many articles that I've seen on the internet talking about using knowledge, GraphRag. When they talk about GraphRag, actually all they're doing is just finding the nearest neighbors of the words that you find, k-nearest neighbors, right? In the knowledge graph, or you just use a graph database and find the neighboring terms in the graph and use that for search and answering the question. That is, that too is GraphRag. But the GraphRag that I'm talking about is this more nuanced GraphRag in which you use this complex structure of human knowledge, in which you leverage and you pre-create these write-ups in your knowledge, because that makes it very, very powerful. And you can see it We have done the paper reading for GraphRag. So if you go back and look at one of our prior sessions, we did more than 6 months ago, 8 months ago when this whole thing came out. 1 second. But I want to round this off with one final thought. This is all very nice to say that having a knowledge graph is most wonderful. But how do we create it? As I said, creating it is an arduous task, right? You have to work very, very hard. It's very labor intensive. So it was still before LLMs came. To the extent that large language models can understand text, they're language understanding machines. One of the bonanzas of the emergence of powerful language models is that this task, this very tedious task, has been automated. You can give it the document, you can let it shred, and you can have it extract the tuples, right? And the good news and bad news. Good news is that it expedites the work. Bad news is it's a bit noisy. It does sort of put in some tuples that you would say, really, do I want to put it in my knowledge graph, right? So there's a sort of noise injection. It is not as clean a knowledge graph as what just pure through human effort and careful review would have come out. But another way to look at it is that if you can create a knowledge graph and let us say you can review it yourself, then it would be much better. In practice, you can't. What happens is that you will get a tool that does knowledge graph. You'll plug it into your RAG pipeline. And the people who are plugging it in and the people who are usually not experts at graph theory and all of this, right? So they say, okay, it's a black box. Let's just plug it in and let it do its magic. Which is the more dominant form that I have seen, or the way I've seen people use it. Right? It's quite interesting, actually, that when we do that, of course, we just scratch the surface. There is a lot of unrealized potential you leave on the table. So much you could have done if you sort of went a little bit deeper and understood this whole theory, the whole thing really well. So that is it. So they talk about GraphRag and what's the advantages of GraphRag? A node connectivity captures and reasons over relationship between entities. No brainer, right? Hierarchical knowledge management. We just talked about that. Context enrichment. We talked about that. What is its limitation? Limitation is scalability. Well, I wouldn't say it's a scalability problem in modern GPU. What I would say is indexing your documents and creating the GraphRag is expensive. I remember the last time we were giving a GraphRag course. I mean, the whole the course that's about to start on February 20th. One of our participants went happily to the company and said, we need to do this. It leads to much better results, and showed that you take this 10 documents and you do all of this and the results are so much better. The enterprise said, all right, we go all in. And they were using OpenAI to do this tuple extraction. And 24 hours later, they had a bill of thousands, right? And as you can imagine, the higher ups were not amused. Unexpected bill. So that is a cost factor. But I think that cost factor today is moot, because if there has been one big development recently, it's that very high quality, very high reasoning models are now tiny, and you can run them on your local hardware, right? As you guys know, just in the last couple of days, UC Berkeley has come out with a tiny model, 1.5 billion parameter, a reasoning model that apparently is at par with O1, or in most things is at par with O1, the reasoning model, the frontier class reasoning model from OpenAI. I don't know what it is. Just look it up. Berkeley just came out with it, right? After DeepSeek, of course, the world has changed. Everybody has realized that here is a new way of doing it, and if you do it using reinforcement learning, the way DeepSeek paper explains it, then you can train very small models to reason really, really well. And so the floodgates have opened. And I think we are going to, by the way, all of these things that I'm talking about, we are doing it in our lab, and we are also obviously, I mean, this is a very short conversation here, and we are coming to the end of it, but let me just give you a first-hand experience. When you do this locally, you enable AI, like you bring these three components in. Let's bring the three big ingredients. What this paper calls modular RAG, namely retrieving from multiple sources and tools. Then graph RAG, namely putting a knowledge graph in there. But when I mean knowledge graph, I don't mean just putting a graph database or just a simple knowledge graph. I mean in the sense that you actually leverage the properties of complex graphs, the community, and so on and so forth. And then when you bring in the AI agents, it really leads to such a powerful RAG experience that it becomes too obvious that if you don't use it, there is a huge opportunity cost for not doing it. The downside, so what I would say is the limitations is scalability, data dependency, high quality data is essential. Now, well, sort of one good thing is if you're doing it for intranet, for enterprise use cases, generally the quality of data is a little bit better than just web scrape data. Right? So depending upon your use case, it is true. If you make a graph RAG of common crawl on the internet, you need a lot of people and tools to clean that data up. Right? A knowledge graph may not be as high quality. So that's a point I suppose they're making. Complexity of integration. Of course, now your architecture gets more complex. One more pretty heavyweight component to add to your system. And then finally, agentic RAG. Agentic RAG. So what is an agent? We keep talking about agents as though everybody seems to know agents. So I asked one of the kids in my neighborhood, I said, what is an AI agent? They said, we know it, of course, the Matrix, the movie Matrix, right? So we all have our own private notion of what an AI agent is. But so I'll just formalize what's an AI agent. AI agent is a piece of autonomous intelligence that can reason and that engages with an environment in which it exists. It interacts with the environment formally through sensors and actuators. Right? So it gets stimuli from the environment. For example, it could be a camera, and it does something to the environment. Those are actuators. Now today, so that's a formal definition of an AI agent. And today we create agentic systems. By the way, when I mean agent, I rarely mean one agent. I always mean multi-agent system, because the magic of agent is not in one agent. The magic of agent is in creating a crew or a team of agents that collaboratively solve your problem, right? So in the world of LLM now, the reasoner, the intelligence, is your LLM with suitable prompts and character and so on and so forth, goals and whatnot, right? For example, Crew AI defines an agent to be something that has a role, a backstory, a pretty backstory to give it character, and then a goal, right? So first two are very necessary. A goal could be dynamically discovered during the execution of the task, right? And so the LLM is the reasoner, and in the world, as we are doing agentic frameworks that use LLM as the core, they tend to club sensors, actuators, and all of this together, and they just use the word tools. So agents runs on three legs: the agent, the LLM itself, the reasoning engine, and of course, with when we talk about autonomous decision making or autonomous intelligence, literally a renaissance of reasoning agents that are emerging, reasoning LLMs that are emerging on the scene is the biggest boon you can have, right? And it not only does wonders to agents, it does wonders to RAG itself, the RAG architecture. The second piece is, of course, the tooling. The better the tools agents have access to, the better. In this particular case, the RAG, it is the tools that is baked into RAG. Right? For example, it's the retrieval tools and the LLM itself. Then then the other aspect is the agentic reasoning itself. How did you decompose the tasks, the responsibilities, the roles? What is the orchestration and so on and so forth between them, collaboration between them? So that is it. What are the advantages? Let's see what this paper mentions. It says that the key characteristics of agentic RAG include agents independently evaluate and manage retrieval strategies, etc. Makes sense. Right? Iterative refinement and workflow optimization. So you can sort of keep going back and forth. If the answer doesn't look good, it may say, okay, let me verify that this answer is backed by data. If not, then let's bring more data and so forth. Right? Dynamically orchestrate tasks, etc. The disadvantages: coordination complexity, computational overhead. Now you might say that in favor of the naive RAG, or at least my definition of naive RAG is at least semantic embedding, or what they call advanced RAG. Semantic embedding plus an LLM is the sheer simplicity of it and the relatively high performance and throughput of that RAG system. It is by far the most deployed or adopted because it is so easy to get there, right? One of the things that I will be doing in the session that will start at 7 is I will be giving code demos, how easy it is to create that vector database, semantic embedding, and maybe I can do it right now if anybody is interested, and do RAG over it. Quite literally, like 4 lines, 5 lines of code it is these days, thanks to this very mature RAG libraries that have emerged on the scene. In this particular case, I'll be using Llama Index to illustrate the point. That they exist, and to the extent that they exist, using RAG has become a no-brainer. Next question. But on the other hand, the more you go all out, you have a whole heterogeneous indices, sources of data, you have agents, and you have knowledge graph. You do have computational overhead. A lot of the computational overhead, you notice, are sort of the inference time computational overhead. And the whole question is it worth paying? And so the way people solve this problem is using a crucial first step. You need one agent whose job is to sit upon a classifier model and take the query through the classifier model and let the classifier model tell you exactly what this query is about and what the complexity of the query is. If it is a very simple query that an LLM can answer, then you can actually short circuit and go straight to the LLM. Forget about even your retrieval system, right? Yeah. And then if it needs some degree of sophistication, but nevertheless is a single hop answer, you can get some documents and answer it. The agent can then harness the right amount of resources to get it and put it through the LLM, look at the answer and say, yeah, this answer is good enough. It does answer the question in view of the facts and in view of the query. Let it go through. Or if it is a multi-hop answer, then it can orchestrate the multi-hops, right? The step-by-step answering, right? For example, if you say, who was the there is a classic question. How many, suppose I were to ask, how many stairs exist in the house where, in the house of the author of the book X? Now, that is unlikely that there is any one document that talks about book X, talks about the author, talks about the author's home and the number of stairs, unless the biographer went to that extent, right? Which would be likely. So the likely thing is it's a multi-hop question. And the agent would say, okay, let's break it down. First, let's figure out who in the world is the author of X. So once you get the author of X, then it may decide, and this is the reason and act thinking. It may say that, okay, I acted upon that. Now let me reason. Oh, I need to figure out where did X live? Where is the house of X? Okay, this is the house. The house exists. Now it will say, okay, is there any documentation about the house of X? Is there any, like, is it a museum that is described in some document? And then it would look through that document. And it would then come back and say, all right, according to this, the number of stairs is so much. So it's a multi-hop, and it's one of those situations where agentic reasoning actually shines very well. It does very well because it can cycle through iteratively and divide the job into subtasks, which is the hallmark of agentic reasoning. Plan it out, divide it into subtasks, and then solve it. Right? And for example, to answer 2 of the questions, you might be able to get it locally, but to know exactly how many stairs were there in that particular house, it might decide to go on the internet and search it out. So that is it. So that's all I would say. This paper has one nice thing I noticed at the end. So these are the paradigms that it mentions: naive RAG, advanced RAG, modular RAG, graph RAG, agentic RAG. I believe we have covered all of those and explained those. It says that agentic RAG is a paradigm shift. I would imagine that once you know about AI agents and the power of it, 2025 is the year of the agents. Everybody seems to have woken up on New Year's Day with one commitment for the year. We will do AI agents, right? This seems to be a collective commitment within the AI community, right? The promise of the year or the resolution of the year. Right. So, and once you know AI agents, it's inevitable that you'll take it everywhere, in particular, the dominant use case, namely RAG. So when you do agentic planning, what are the dominant pieces of agentic RAG, agents? Of course, agents there's a LLM, the reasoner, that's the LLM. It needs memory, that goes without saying. It needs to preserve state, remember things, short-term, long-term memory. The quality of agentic reasoning is planning and task decomposition, which it sort of doesn't mention, and reflect upon it. Like it gets something, says, okay, is it what I want? Is this the way to proceed? And so forth. So self-refinement and critique are the hallmark, and planning and task decomposition are the hallmark of agentic reasoning. Then agents use tools, as we said. How do they engage with the environment? Through tools, right? So then you have tools. So that's what they mention as agent. So there are multiple ways. They go into some examples of it. But if you're familiar with agents, they should look very, very familiar. Now they go into a taxonomy, which frankly I didn't find too useful. But let's just say that if you build agentic RAG, most of the time, given your use case, it will become obvious to you how to use agents. Go ahead.
Yes. Why is it the case that an AI agent comprises of a LLM versus multiple agents having a dedicated, a central LLM?
Oh no! In reality, they share the same LLM in a stateless way, right? So what happens is when you build agentic system, the simplest way is just have one LLM, but you just pretend that every agent has its own LLM. Because you can pretend you're using the LLM in a stateless way, stateless manner, right? So they can all have their reuse or share the same LLM. But in reality, what happens is that, see, if you use a frontier model, the inference cost is high, whether you use in the cloud or you use locally, right? So it is what you do is, and this is where agentic thing comes in very useful. For many, many tasks, simple LLMs, small LLMs are just good enough. So what we do in our case here at SupportVectors is that we look at every agent, and we have a small repertoire of LLMs. Some of them are generic, just straight downloaded from Hugging Face LLMs of different sizes and some of them are fine-tuned LLMs for specific purposes, right? And with domain adaptations. And then to each agent, when we decide the agent, we bind the appropriate LLM, right? And so the repertoire of LLMs all setting upon our inference system, in our case, it's a RayServe with VLLM on which it is running. So then the usual things happen, right? So that's how you build sort of more elaborate multi-agent systems. And I would say, if you look from a multi-agent system perspective, a RAG is almost a no-brainer use case. And when you look from a RAG perspective, the fact that the epitome of RAG technology would be to use all three, to use hybrid retrieval systems, to use graph RAG, and to use agentic RAG. agents to use knowledge graphs with community detection and those pre-summaries, etc., in a more powerful way, and then to use AI agents. So that is what the whole paper is about. It has a few more detail, though I would argue that everybody, like once you become expert at it, you might want to write it slightly differently. The great contribution of this paper, the reason I liked it is that at least it puts all of those things in one place. So you can sort of glance through it, and it makes for a good sort of a survey of the RAG topic. If we can use it to survey the topic of RAG, which we have done. And so that is it. And now I'll take questions.
So the question I had is for graph RAG, can it combine structured and unstructured data? Unstructured data for sure, but what about structured data?
See, the answer is captured in one word. Can you make meaningful triplet out of it? For example, entity, relationship, entity. If your structured data admits such a relationship, then of course. But if your structured data doesn't admit that, then it's pointless. Well, how will you make a graph? You wouldn't even be able to build a graph.
Follow-up question to that. So making it more realistic, let's say I have a SQL database and a couple of tables, etc., etc. To actually make sense of this tuple, is there a way that I can say, hey, these are the different tables, these are different entities, and these are different relationships, and then feed it in?
See, what you do with, and this is a RAG question, code generation with SQL. SQL generation is a topic in itself in RAG. So when you do the bootcamp, we will show you. So no, let me answer that. So the way you do that, because in that you'll find a more elaborate answer. See, what we do is we say that don't do the SQL generation the way, for example, we see in some of the open source project. It sort of works for small schemas. It doesn't actually work. The more elaborate way that we do it is, or we teach you to do it, and we make you do it, is this. What we say is, see, you have a schema. Reality, the de facto schema and what is the schema that an entity relationship tool will discover are different. For example, there may be, quite often, you'll notice that there will be a table which seems to be the appropriate place to keep the data, but it is kept somewhere else, which also has table, but the columns are not named so aligned with it. Nevertheless, everybody agreed, let's keep data there, right? So the schema, if you just give an LLM to study the schema and infer, it generates not so good queries. Now to the, so what you typically do, or what we do, is we take the schema and then we create a lot of things from it. We ask LLMs to create descriptions because columns are not described. So to generate descriptions of the schema, then we just say, developers, could you just review it? Descriptions of the table, textual descriptions, because you're using a language understanding machine. The more text you can pre-generate and index in your vector database, the better will be your SQL query generation. You do that, and then what we do is we ask it to do, just as in pandas you do describe, it will do summarization of the table. We actually, one of the things that we do is we make statistics out of the table, especially the numerical columns and the unique values. And we create descriptions of that. We index that also, because it tells you how populated that table is and where information is likely to be present. We index that also. Then we look for aggregation. So what happens is sometimes you write queries that are analytical query. You do aggregation along certain dimensions of certain facts, right? We actually use LLM to infer dimensions and facts. Sort of say that if this is a OLTP schema with these relationship and intersections, what would be a coherent way of thinking of it as a snowflake or as a star schema, without doing that actually, but within this infer, how would you think of it like that? And therefore, what would your aggregate dimensions be? Believe it, when you see, you can systematically use a LLM to pre-think all of these things prior to runtime. And then when you index all of this into the vector database, and then when you come back and write your query, you say that, okay, write me a good SQL query to do my job. It works very well. To the question that can you knowledge graph it? The textual descriptions that came out, yes, you could knowledge graph. right? But knowledge graph is very specific term. It's not any graph. What you have to see, a relational OLTP, a relational schema is inherently a graph, but it is not a knowledge graph.
Correct.
Right? And so the knowledge graph technology that we are referring to is not directly applicable to this, except in the sense that I said.
So again, maybe let me simplify that question.
Yeah.
Given a schema,
Yeah.
if the end goal is to create the semantic definitions and the knowledge graph out of it, what's the best way?
Then you can do that. Yes, as I said, I literally gave you that. What you do is you use LLMs to infer the functionality of a table,
Okay.
Create descriptions of each column, right?
Sure.
And then say this column belongs to table this. Now, column has a description, table has a description.
Right.
And you now have a knowledge graph that you can use.
Okay. So maybe I'll be more prescriptive this time after hearing what you've said. So let's say I have a regular schema. Okay. Not a lot of metadata, not of information. So maybe first and foremost, I put metadata onto the schema definitions like the tables, etc. Like these are different fields, what it stands for. Maybe that can be used for doing entity extraction.
Right.
Then you have different tables relationships, assuming it's an OLTP schema.
Yeah.
Okay. So then it kind of knows that this table is a person table. It has first name, last name, etc.
Yeah, you can do that.
That's part of the table metadata itself.
Right.
Okay. And then you have, let's say another, entity called, let's say album, which is, let's say, it's a musician or is a person publishing some albums. And then you have a relationship, which is, foreign key, etc. So now, would it be fair to say that our job is to make sure that the LLM can discover the entities, what the name, what it stands for, and the relationships?
Absolutely.
To the different tables?
Absolutely. Actually, what happens is most schemas, most people, I mean, you get the schema, you get the columns and tables. You really don't get the comments, the descriptions there.
Correct.
Look at enterprise. Like if you look at, they will have like 10,000 tables.
Correct.
And most of them you would be lucky if the column names are descriptive enough.
Exactly.
Right? It turns out that the LLMs have, because they have seen so many schemas, they are extraordinarily good at inferring that. So you pre-create all of those descriptions. My experience is it goes a long way in improving your SQL query generation after that.
Okay.
So do that.
Got it. And now a follow-up question. So assuming that the LLM has understood what the quote-unquote OLTP schema looks like, and you mentioned that it will also run some aggregates and so on. Now, obviously, running that on an OLTP is not efficient.
No, it won't run. It will infer from the schema what are likely to be the
cardinality to infer. You'll have to run some query to infer the cardinality.
So you can give it a tool. Usually you don't, because it can swamp unless you are giving it a dev database. We can always give it a dev instance, right, which hardly has anything in it.
Okay.
And
so
you can
give some representative data.
Representative.
Not the full data set.
Oh no, you don't do that.
So you take maybe like a secondary read replica, copy to maybe some staging training environment, and then give it some sample data to see them.
See, what do you do for developers? This is for human developers, you do exactly that, right?
Yeah.
You will give it the smallest data that is still representative of production.
Yeah, got it. Yeah.
Right?
Okay.
And then you let it work with that.
Yeah, got it. Thank you.
Right. And it does work. So actually, SQL generation is one of the more powerful use cases of RAG. The last time, from our last batch of RAG, actually, in that room there, came a team, without naming the company. They have done such a marvelous implementation of RAG on SQL and they presented, there's a benchmark, TPC data science benchmark, and they actually sailed through it in flying colors. And in an Apache conference, they got quite an ovation for their work. Right? So doing it right, see, here's the thing, RAG, in my opinion, is a missed opportunity. Most people think, hey, it's 5 lines of code. Right? See, I did RAG. It just speaks to the problem with GenAI. POCs are extraordinarily easy to do. I would imagine that a 10-year-old can do a POC of RAG, or an 8-year-old can do a POC of RAG. Doing it at scale and getting it right, not leaving opportunity on the table, that is extraordinarily hard, because that takes grit, that takes patience, that takes hard work and thinking, right? And That's why, of course. The reason I took this survey of RAG is I wanted people to know that this field is actually a big field. It's really, really worth learning well. I do have a vested interest, as I said, in in saying that because I'm just about to, as you know, I apologize for this. And here's my marketing spiel. I'm about to start a course on RAG on 20th.
Yeah.
Right? So if you're interested, by all means, if you really want to get into RAG, do that. And why would you? I mean, the question is not whether you're interested in RAG. Question is, do you really understand how much depth and breadth there is to the topic of RAG? And do you really want to understand the whole of it properly? So you can build really powerful RAG systems. That's a question.
Mm-hmm.
So Asif, I would like to mention here that I took the RAG course with you in 2023, and I've implemented especially the hybrid search to actually tackle the problem of the acronyms not showing up in the search using what I learned in the course. And I know the quality of course, it's really great. And there are some other challenges any enterprise face, right? For example, if there are two documents similar but from a different department or different policies, right? And usually the FAQs don't really reiterate the topic of the document, like when does this begin, when does this close. So they use pronouns like that. In that sense, if you chunk them, you really can end up with a chunk that does not have any context. So problems like this, do you think GraphRag will address?
Yes, actually, Haripriya, thank you for the endorsement. And so two things have happened. 2023 feels practically ancient history now. You were in one of the earliest batches of the RAG course. And at that time, what we didn't do in that particular course, I remember, we did not do separation of thoughts, what I call. It's a technique I taught. No one does it. We do it. You said that, see, a chunk can just abruptly stop in the middle of a important thought, and the thought needs to be continued to make sense. That's the main problem you're referring to. One of the techniques we do with RAG, and so this is partly knowledge graph to directly answer your question, does make it much better because it pulls in the missing pieces, because it will pull in the other chunk which is needed to answer the question. That is true. The other thing that we do is that we rewrite source raw documents in such a way, we use LLMs to rewrite raw documents such that we separate out the thoughts. Instead of, we not only chunk the original document, where they will, no matter how good a chunking strategy you use, hierarchical chunking, semantic chunking, this chunking, that chunking, nevertheless, it will be imperfect. The fundamental disconnect is chunking is ultimately a size problem, whereas human thought is size agnostic. Sometimes you can express a thought in a one-liner. Sometimes a thought takes 2 pages to express, right? So that's a fundamental disconnect. And so what we do is we reformulate the text, all the text, and we try to separate out the key points. And then we our chunks are each key points that we find in the document. And that goes a long way in addressing the problem you mentioned, Haripriya. That, along with knowledge graph, it makes a world of difference.
Hi, Asif. Can you hear me?
Yeah, sure. Go ahead, Shira.
So I believe it might have gotten answered already, but just wanted to make sure I hear on this one. So you were reading some papers or some commentary by somebody saying that you can always ground your LLM answers in the graph rag, actually, not graph rag, in the graph, actually. So
no, I don't understand. I don't follow. Please repeat that again.
So not the grounding the LLM answers with the truth which is in the graph. So after
not in the graph only, not in the graph.
No,
because
I mean, the sense is wherever your source of truth is, which is kind of, sometimes you give the guardrails to the LLM itself, and then when you get an answer, you check against the guardrail again, saying, okay, has it remained in the context that I supplied, and check with whatever the answer you got. So is that what they're saying when they say ground the answers in the graph knowledge? It kind of makes sense that I don't want you to give me anything. I don't want you to create anything probabilistic here, because I gave you specific instructions that not to go out of the sandbox. Is that what's going on here?
See, there are two aspects to it. One thing is a broader statement. Never discard the source of truth data, right? A graph rag, and like for example, I said create derivative documents in which key points are separated. These are what I call derivative artifacts. A knowledge graph is a derivative artifact because you're summarizing the little communities in there. Yes, it is true that most questions, their answers pretty much are pre-baked. It's like, buying a dinner, frozen dinner from a grocery store. The last stage is just to microwave it. So that is a close analogy to how knowledge graphs help you answer a question. Nevertheless, to prevent hallucination anywhere, you should always pull in the raw chunks as part of your search result and force the LLM to point to one of the raw chunks as evidence of everything it says. In other words, it must have back references. If you go to Perplexity, for example, which I would consider an amazing and at-scale implementation of RAG. I mean, think about it. People say RAG can be done in 4 lines, yet Perplexity has no competitor that I know of that executes at that level of scale and thoroughness. Right? What have they done? They have done RAG really well. Right? And if you look at one of the things, they go quite a distance to prevent hallucination. You will see that everything that is said in their answer has back references to source documents. That should be your gold standard. And again, the broader statement I would still make, never derive your answers only from derivative artifacts, rely on your answers only from derivative. Always make it point back to the source, because hallucination can have pretty drastic consequences. It is the one problem that you have to avoid with RAG. All right, guys, I don't see any other thing on chat. Mike, I apologize. I didn't see that message about the Zoom. Was it bad throughout, or did it get better along the way?
No, it got better, Asif. Thank you so much. Yeah, it wasn't a big problem. It was not.
Okay.
So another question, Asif, and you can answer as topical as possible, that's fine. But, from the discussion, what I feel is, for grounding, we use LLM. For document processing, we use LLM. Doesn't it beat the optimization of the retrieval process itself and slamming everything on LLM? Will it pose some, cost token?
Yes, it does. That's why, absolutely, that's a very valid problem. And as I said, right, what we recommend in our courses now is not to use one LLM, but to use a collection of them. We use very tiny LLMs in-house. Then we use small LLMs that we have actually done domain adaptation and specific fine-tuning for. Right? We use reasoning LLMs, and we keep frontier LLMs, the ones that you call over that. Only if the data is not sensitive, you can, because there'll be a knowledge exfiltration. And if you cannot do without in-house. And today it is hard to argue why in the world would you go to a frontier LLM. If you have the hardware to host a powerful model in-house, what you do is, that's why I said that right in the beginning, you need an agent to determine which of the resources to pull up to do that. The second part is that, see, knowledge graph creation, and a lot of this is pre-processing. It's a one-time cost. It's a capital cost. Once you have a knowledge graph, it exists. It will be used for every single query that goes through the pipeline, right? And it returns pretty fast from that. But the one-time indexing and creation of the knowledge graph, yes. If you're using one of those cloud services, let me know which one. I'll buy their stocks.
And also document updation in an enterprise. There are daily updates to the documents.
Yeah.
At least for 10% of the documents, they are updated. And there is a complete full refresh on a weekly basis. So which means the knowledge graph has to be recreated in each of these scenarios, right?
Yeah, that is right. I mean, we don't recommend weekly refresh of knowledge. We say that incremental you should keep doing on a daily basis. Do a full thing till there is evidence of degradation. Don't do it otherwise. See, one evidence of degradation would be that there is an overwhelming amount of old release documents and a new release has happened, and you shouldn't be answering questions from the documents of the previous release of the product. That should be a trigger, because that refreshing your entire knowledge base at that moment and your RAG system, flushing it out and redoing it, there is a good cause, and essentially something will pay for it, namely your product sales will pay for it.
Sorry. Yeah, go ahead.
Just completing my thought here. So even for a daily updates, right? If it's just chunking, maybe one document can go 10 chunks. Now an updated document has only 7 chunks. But if it's a knowledge graph, the link, the entities and edges, nodes and edges have to be refreshed for everything that's connected to the document. Right? So it's
No, it doesn't. It's a additive. The graph is additive, and at some point you do have to do resummarizations sometimes and that. But generally, right? Graph, it is a bit more cost. It's not free. It does add cost, but unless you're adding voluminous amounts of completely fresh knowledge, it is not worth redoing your entire knowledge graph. Because see, as they say, right, there's nothing new under the sun. From a knowledge perspective, all the new documents that will come will talk about the same topics. So use that cautiously.
Asif, I have a question regarding the, is there a way to get some, I think you referred to it in the beginning, whether along with the tokens, there is some entropy measure, probability measure that comes out?
You read the Dragon paper, a very bright person within our community, Atisha, who is taking actually she's taking the RAG course. She did the paper reading for Dragon. Read the Dragon paper reading from one of our prior sessions.
Got it. Thank you.
Any other questions, guys? And we can stop the recording for this session.